Okay, in this video we're going to look at internal resistance. Internal resistance is one of those things I have a bit of a bone to pick about, really, because I think this concept is always overly confused by the excessive equations that are required. And hopefully I'll show you that just a good understanding of circuits and Kirchhoff's laws actually negate the need to learn a lot of this, because if you understand Kirchhoff's laws and you can apply them, then all of this is fairly moot. Apart from the experimental procedure, which you'll get practice of doing anyway in lesson. But see how you feel about this as we go along. Well, what is internal resistance? Well, internal resistance is basically resistance that's built into any cell or battery. And usually we represent it like this. So in any circuit, what we would expect is there to be a box around the cell and a resistor in that box, which is representing essentially a battery or cell with an internal resistance. This resistor being a little r, representing the internal resistance of that cell. So normally we put this in a circuit like so. And what we could do is we could essentially observe that, let's say for example, we've got a battery which quotes an EMF to us of, let's say, 1.5 volts. And we put our voltmeter across this resistor here, the big one that's in the circuit, and we only get out 1.4 volts. Well, that's a bit of a problem, because we're like, well, where has that voltage gone? And in previous lessons, in previous concepts, we've gone back and we've said, oh, well, it's energy lost in the wires. Well, in this case, it's not just energy lost in the wires, it's more likely to be energy lost or lost volts in this resistor here. Now, utilizing Kirchhoff's second law, the loops about PDs and EMFs in a loop. Now, we've already suggested that the EMF of this battery should be 1.5 volts. We're only getting 1.4 volts. The only other resistor in this circuit is the internal resistance. And so, as a result, we would expect that to be the cause of our lost volts, being, in this case, the 0.1 volts that's missing to add up for our loop. So in this case, really, like I said before, it's just a simple understanding of Kirchhoff's second law. The fact that we've got an EMF, and actually we've got an internal resistor and an external resistor, which are causing PDs, have PDs across each of them retrospectively. So it's actually, this circuit is really no different than something like this, for example. So let's say I take this internal resistance out and draw in two resistors. The previous circuit I drew is no different than this one. If I asked you, if I had a question that had a voltmeter across this one and a voltmeter across this one, you could easily say, right, okay, if this one's got 1.4 volts across it, then from Kirchhoff's second law, we know that that must be 0.1 volts. And all the same electrical circuit rules apply. Kirchhoff's first law, the current. The current running through this battery is the same as the current running through this. So if the resistor just happens to be in the battery, as we suggested before, then the current running through there is the same, sorry, I put it the right way around. The current running through there is the same as the current running through there. There is no difference because it's in series. So whatever the total current is in the circuit is whatever the total current is going to be in that battery or cell, and the internal resistor retrospectively. So there's a lot of equations that are bandied around that you need to know about, because it expects you just to throw numbers into them and not really understand where they come from. We're going to explain where they come from here now. So there's the first equation that you're expected to know is this one, that the EMF is equal to V plus IR, where this V here is this voltage that you get out across the external circuit. okay? So that's the external PD that you're getting out across that circuit. The EMF is this value right here. That's the quoted value of the power supply, or the cell in this case, that should be being produced. And then we've got our lost volts here across our voltmeter, which is attributed to this IR term over here. So that's IR, where little r is the internal resistance. So this is a bit of a fudge. It's basically just saying what we already knew from Kirchhoff's second law, is that what we put in is what we get out, because all this represents is a bit of Ohm's law, because V is equal to I times R in Ohm's law, so the PD across this resistor is I times R. That's the current in the circuit. So what can we say about this one then? Well, that's the same thing. You could just say that that one is IR, and that one, this one here, if we then give this a large R, as it often is, then we can say that this V is equal to I times by R. And so you could then write this as EMF is equal to IR plus IR. And then you can factorize that, and you end up with a very simple, more simple version, which is IR plus R, which is another of the expected equations for you to use. But again, all of this is just an understanding of the circuit rules. All this is, these two equations here, are just equations that have been amalgamated together to let you throw numbers in to get to grips with internal resistance. If you have a clear understanding of the circuit rules from before this video, then you shouldn't really have a problem with a lot of these concepts that I'm banding around here. Okay, so that's the general equations and how all the concepts link together. You've got two resistors in a circuit, and that's what happens there. Now, what we can look at is, how do we actually measure internal resistance, and what's the common methodology to do that? Well, we use a very similar setup as we have before, except the only difference is that I attach a rheostat or a variable resistor in here. And what I'm looking to measure is the voltage out across that resistor there. And so what we have is a situation where we can adjust the resistance here. Now normally we'd expect, if we have one resistor in a circuit, we would not expect the PD to change, because we've got one resistor and it's all on its own. All the EMF is going to be out across this resistor right here. However, because of this small, tiny internal resistance, that is not going to be observed. So what will be observed is, as I change the resistance of this, then the PD across this will also change, because I've got another resistor in the circuit. So what we've got here is we've got a situation where we have a look at a graph that we might obtain. Now this time, strangely enough, we actually do a V against I graph. The reason for that is because I've got a fixed battery. I'm not changing the voltage this time. This time, I'm changing the resistance. By changing the resistance, I change the current. So the current is what I'm changing here. That's my independent variable. My dependent variable is the voltage that I get out across my battery. So what we would expect to see as I increase the resistance and drop the current, then we start off with a nice high value, and we go all the way down like a straight line, just like that. Now, what can we find out about this, this graph, or can we use this graph to find out? Well, quite simply, the gradient of the graph, V over I, that's R. This value right here is really important because that's where the line crosses the y-axis is the y-intercept, which also is equal to the EMF. And that is a really, really important value to get to grips with. So you can get the EMF from this graph. You can also get the internal resistance of this resistor by using and utilizing this circuit. We're going to build this circuit in lesson. We're going to hopefully display this graph, and hopefully the EMF we get out from our y-intercept will give us something meaningful, and we'll be able to compare that to the battery or the cell that we are obtaining our EMF from. Okay, so that's a brief rundown of internal resistance. You'll get plenty of practice on that, and like I've said, if you have a good understanding of circuit rules, it's not going to be too difficult for you. If you want to go back and have a look at Kirchhoff's first and second law rules and Ohm's law, because all of this ties together, would be beneficial to help you deal with some of the stuff that I've just thrown at you there.